Hello and welcome. Today we're looking at electrophilic aromatic substitution reaction mechanism. And basically what happens is that you start with an aromatic compound, like benzene in this case, and then you react that with an electrophile, so E+. Remember, electrophiles equals to Lewis acids. That means they accept electron pairs. And what's basically going to happen is that one of the protons on the aromatic carbon gets substituted with the electrophile. You lose the hydrogen and then replace it with the electrophile. So that's electrophilic aromatic substitution. In this particular reaction, we're using Br2 and FeBr3, so that's a metal catalyst. And basically what happens is that you end up generating a Br plus electrophile. So Br2 plus FeBr3 gives you Br plus, which then will substitute the hydrogen, and now instead of the E, we're going to have, instead of that, electrophile. In this case, the electrophile is bromine, so you end up substituting the hydrogen with the bromine. So mechanism. So step number 1 is a reaction between bromine, which is Br2, so we write it as Br plus FeBr3, which is a Lewis acid. And what happens is that the bond between bromine and bromine breaks, and the electrons goes to one of the Br, and then that connects, attaches itself to FeBr3. So you end up with FeBr4 minus, because of that electron, because of those two electrons. But now on the other side, you're remaining with Br plus, because that bromine loses the electron, like the bonds that were the electrons that were used for the bonds flows to the other bromine, and now this bromine becomes the electrophile. So step number 1 is generation of the Br plus electrophile. Step number 2, we now use our aromatic compound. In this case, we have benzene. For the sake of this mechanism, I'm going to show the 2 hydrogens on this carbon. We know that all the carbons on this aromatic compound have hydrogen, but I'm just going to focus on those 2. And then react that with the bromonium ion generated from step number 1. And as you know, bromonium ion is a Lewis acid. That means it will accept electron pair. And now the benzene has higher electron density. It will use one of its double bonds to attack the bromonium ion. So you end up attacking the bromonium ion like that. Then that gives you this intermediate. We still have these 2 double bonds staying in place, but now on this part, on these carbons, we still have the green hydrogens, but now we have bromine connected to that carbon. And this other carbon has a positive charge because the electrons that were used for the double bond were used to make a bond with that bromine. And that intermediate is called Wieland intermediate. So it's almost like a carbocation. And now for step number 3, we use this Wieland intermediate, which is right here. And now this step involves the loss of H+, so minus H+. We lose proton or hydrogen ions, and basically what's going to happen is that we lose that hydrogen, and then the electrons that were used for the carbon-hydrogen bond will flow back to make a double bond and neutralize the positive charge intermediate, and you end up with aromatic compound. So the driving force of this step is the formation of aromaticity, which is stable. So now we form that double bond, and we only have the other hydrogen. Of course, we still have hydrogens on the other carbons that I'm not showing, and that's going to be the product. So just a quick review. In electrophilic aromatic substitution reaction mechanism, first of all, the hydrogen is replaced with the electrophile in this case, if you're using Br2 and FeBr3, the electrophile is Br+, so you end up substituting the hydrogen with Br. And the mechanism involves 3 steps. Step number 1, formation of the bromonium ion intermediate, and that's where Br2 reacts with FeBr3 to give you FeBr4 minus, remember the minus, plus the bromonium, plus the Br+. Then step number 2, we now use the Br+ electrophile to react with the benzene. So we'll call that a nucleophilic attack of the Br+ by benzene. And you end up forming a Wieland intermediate where this carbon here has a positive charge and the other carbon now is connected to the Br. And then the last step is the loss of proton or hydrogen ions. So you lose this hydrogen, and as you do that, you end up forming a double bond in that position here, and therefore you restore aromaticity, and that's the end of the reaction mechanism.